So let's start with just marginal cost. Given marginal cost and an initial condition, in other words, a certain criteria that has to be satisfied. So if we have the derivative of something, we can go backwards to get the original something by anti-differentiation. So if we have marginal cost and an initial condition, we can go backwards, which is not truly a technical math word, but we'll put it in quotes then, with anti-differentiation to get, or actually to recover, to go find, to determine. So that's why I call that word recover, the original cost function. Okay, some examples like this will be found on page 807, and we're going to do, we might as well do something that's got some meat to it. Let's do 54. Got plenty of decimals in there, but I hope, Scooter, did it help when you changed everything to decimals with that problem that you asked me about?
Yeah.
Yeah, it made it a lot easier, didn't it? Yeah. Decimals, even though we have to be careful, make sure we don't lose our decimal places and stuff, they can still, we probably still prefer those over fractions. In fact, did anybody used to play the stock game at when you guys were in high school? Did you play the stock game or anything like that where you had to look up stock prices and stuff? Scooter, when you look up your stock prices, weren't they in fractions? Do you remember it?
I don't really remember.
Okay. About 5 years ago or so, they probably were in fractions. And then guess what they did? They put all the stock prices in decimals. They converted all those stock charts that used to be in fractions. It was a kind of a mainstay for reading the stock quotes out of the newspaper. They were always in fractional parts of a dollar. But they have finally turned it over to decimals because we know the decimals are just easier to cope with than fractions are. That's okay. Fractions are still, we still love you, fractions. All right. So see, they're telling us here C prime of x. So they are giving us, in this case, they are giving us marginal cost. And I put this extra 0 before the decimal point. The book doesn't, but I think it needs to be there because I think it's easier to not lose your decimal if you include it. All right, so they gave us this. This is marginal cost. Plus, they also gave us, and I'm going to put it over here on the left-hand column because we're not going to use it right away, but we will use it in a little bit. They gave us an initial condition. And our initial condition is that 10 units cost, in other words, it costs $25 to make 10 units of this particular product. And with that information, we can go backwards and we can find the total cost function. We know marginal cost in this case, and we want to go backwards to find the total cost function. All right, so here's what we're going to do. Here's the symbols that we're going to use. Now, if I remove that prime symbol, now I'm talking total cost, not marginal cost, if I don't have that prime symbol there anymore. Total cost is going to be the antiderivative of all this stuff here. So let's just recopy it all down here. Hope I have enough room without making it squished. Now, what's the variable that we have in our marginal cost? X's. Okay, so when I put my notation at the very end, I'm going to make this dx. Okay, because I need to have that differential. Anytime I write an indefinite integral, I need to have that differential symbol. Everything was in terms of x, so we're going to be anti-differentiating in terms of x also. Oh, I sure am, and that's how things can get messed up. Thank you, ma'am. Because we certainly know that 48 thousandths is not the same thing as 48 hundredths. Because 48 thousandths is about 5 cents, and 48 hundredths is 48 cents, so not the same thing. I need that decimal place in there. Without it, I definitely have a different number. All right. Every one of these, can we use the power rule? Let's see, what's the power here? 3. Okay, can use the power rule. What's the power here? 2. Use the power rule here. What's the power here?
1.
It's a 1. Now, I said I couldn't use the power rule with -1, but nothing said I couldn't. I can use the power rule when I have a positive 1. So we'll be able to do that one. And there's this. When we look at that last term, I'll show you what we're going to look what that will end up being. Okay, let's see if we can do this one without having to write all these separately. All right. So the first one is bring that constant factor across. All right, times. All right. What's it going to be? 1 over what number? 4, because it's 3 plus 1, times x to the 4th. Okay? Okay, good. Okay, bring this constant factor out front. This is going to be 1 over 3 times x to the 3rd plus, all right, what are we going to do here? 1 over 2 times x to the 2 to the 2nd power. And then we have one more term. Right. Well, nope, not 1 over x. In other words, this last term, when I want to anti-differentiate this with respect to x, what am I going to put in here?
25x?
25 hundredths x, right. 0.25x, right. Just not going to fit. All right. And then there's, well, of course, one more thing. What is the last thing we got to put on there?
Plus c.
Plus c. But you know what I'm going to put this time?
Plus x.
No, I don't want to use the same variable as my actual variable. How about k? Is k okay for a constant? Sorry, I had to. Right. Maria's got it. I don't really want to use plus c here because it sure as heck is going to confuse me. I've got c standing for the total cost function. So my arbitrary constant here I'm going to use is k, just because I need to keep it different than the c, or it's really going to be confusing. All right, so let me see if I can write this up here more neatly now. All right, so what we've found out so far is that total cost, we know up to an arbitrary constant. We don't actually know the constant value yet. Oh, that's not right. So it's 15 10,000ths over 4 times x to the 4th plus, was it 33 thousandths over 3 times x to the 3rd. Okay, what was the second power? 8 divided by 2 times x squared plus 0.25x plus an arbitrary constant k. Okay, I think all those are going to go in nice and neat. Let's see, except for the 14. So I got a calculator. Who else needs a calculator? Okay. So we got. I want to just go ahead and I want to make these a little bit easier. Just going to figure out what these numbers are. So 15 10,000ths divided by 4 should give us a nice finite decimal. Okay, I get 0.0000375. Did you guys get that? Mm-hmm. Before the decimal? Yeah. Oh, after, I guess if you're going, yeah, after the decimal. You're right, Maria. Mine came out in scientific notation, but that's the same thing. That's probably easier, okay? The rest of these go in evenly. All right. So now we know the total cost function up to a constant term. We still don't know what our K value is. But tell me what questions you have about that before we go on to figure out what K is.
So is X the units?
X is the number of units that you produce, and C of X will tell you the cost for producing those units, the total cost for producing those units.
So pretty much you're going to, next part of the 25 equals and all that.
Bingo.
With 10 for X and
Bingo. And that will allow us to find us K. Yes. Scooter has figured out how we are now going to find K. In other words, what specific number is K? And if we didn't have our initial condition, we couldn't know. But we do have an initial condition. Our initial condition was 10 units cost $25. So if 10 units cost $25, that is telling us the total cost. In fact, let me go in through here and write this thing empty, because you know how I'm liking empty functions here. If we compute this cost function at 10, we're supposed to get 25 out, because we know that initially. For whatever reason, we know our research, and we know that it costs us $25 for 10 units. Okay, so here's my empty function. This is giving me the total cost for producing X number of units. But I happen to know that if I produce 10 units, it's going to cost me $25. So what I'm going to do is I'm going to go through here and I'm going to put in 10. Now I got to do a lot more math. Thank goodness for calculators. There's I have to be using my slide rule. And I don't know what K is. This value is 25. The cost to produce 10 units is $25. All right. 10 to the 4th times, I should be able to do this. Actually, 10 is actually quite easy to compute with. So this is going to be 3.75 plus 11 plus 2.4 plus 2.5 plus K. And you guys can tell me, you guys might do it all. You may, on your graphing calculator, choose to find all of this as one lump and then plus K. But I just did, multiplying with 10 or powers of 10 is just moving the decimal place. All right, so I should be able to do the rest of this mentally here. Okay, that's right, Scooter. So once we lump all this stuff together here, all these numbers, we plug in 10, this is a number, this is a number, this is a number, this is a number. Add those all together, we get 19.65. Solve for K. And we get K equals 5.35. Oops. So now we know what that constant should be, because we know an initial condition. So our particular K for this particular situation is 5.35. And it would still fit the bill that if we did the derivative, we would get right back to the marginal cost they gave us. Okay, that's called function recovery. So cost function is, one more time. Now I'm starting to look like sixes, so I'm going to end up making it look sloppy. I don't want to do that. So as I'm writing, ask me questions. Oh, well that's a hindrance, isn't it? There we go. Okay. So far so good? You get to try some of these in your homework. Plus, now instead of putting k, we know specifically what k should be. It should be 5.35 for the function recovery.